Hi, in this video we are going to talk about the theoretical background of binary search trees. So let's get started. We have seen so far how to store data in arrays or linked lists, and we see that most of the times it takes linear time to go sequentially, for example, in a linked list. And the question is, can we do better? And the answer is yes, we can reduce this linear time complexity to logarithmic time complexity, which is much better. So binary search tree is used to implement lookup tables. We want to store data. We keep the keys in sorted order so that lookup and other operations can use the principle of binary search. And if you are familiar with what's the difference between linear search and binary search, that's the main point here, that instead of linear time complexity sequentially goes through the array, we can jump at the beginning, in the middle, and check whether in the sorted array it is greater or smaller than the item we are looking for. And on each iteration we discard the half of our data. And this is happening here in the binary search tree. So each comparison allows the operations to skip over half of the tree, so that each lookup, insertion, deletion takes time proportional to the logarithm of the number of items stored in the tree. This is the logarithm time complexity, of course. So this is much better than the linear time required to find items by key in an unsorted array, but slower than the corresponding operations on hash tables. We are going to talk about hash tables because the question is the same. So we now construct a binary search tree, we achieve the logarithmic time complexity, and we again pose the question that can we do better? Can we reach, for example, constant time complexity? And the answer is yes, with the help of hash function and hash tables. So here in binary search tree, an insertion is that if the key is not equal to that of the root, we search the left or right subtrees recursively. The deletion is we can use the soft delete. We do not actually remove the item, just mark it as deleted. It is not so efficient because there may be lots of data that we do not use, we do not need in our tree. So deletion is deleting node with no child. It's very easy, we just set it to null. By the way, all of these operations we will see illustrations, so it will be clear. Here in the theoretical section I just want to tell a few words about it. So deleting a node with one child, we just have to remove the node and replace it with its child. The deleting a node with two children is a bit complex. We have to call the node to be deleted I, and do not delete I directly. Instead, choose either its in-order successor node or its in-order predecessor node j. Copy the value of j to I, then recursively call delete on j until reaching one of the first two cases. What are these cases? When it's become a leaf node, and if it's a leaf node we just have to set it to null. An in-order traversal as a graph gives us the numerical order, and if we make this in-order traversal, then it is going to give us numerical ordering for integers and alphabetical ordering for strings, for example, and the predecessor and the successor is the given node in the in-order traversal. The successor, of course, is the next node, and the predecessor is the previous node. We are going to see it in the illustration. So a few words about the time complexities. We see that the average case complexity, instead of linear, is going to be logarithmic, but the worst case is going to be linear. So the worst case we end up with a linked list, and that's why we are going to talk about balanced binary search trees or AVL trees. In AVL trees the worst case is logarithmic too. Another important parameter is the height of the tree. We usually denote it with h, the length of the path from the root to the deepest node in the tree. This is the definition of the height of a given node. So we should give the height of the tree, and of course the height of the tree is the height of the root node. We should keep it at a minimum, which is h equal to logarithmic n. If the tree is unbalanced, the h equal log n relation is no more valid, and the operation's running time is no more logarithmic. So if we want to search for something, we are not going to be able to find it in logarithmic time, and that's why rebalancing the tree from every insertion will be very, very important. So for how to construct a tree, the first node is trivial. It's going to be the root node, for example 12 in this situation. And whenever we want to insert, for example 4, we have to examine from the root node whether it is greater or smaller than the given node. Here 4 is smaller than 12, so it is going to be the left child of the root node. So in a binary search tree, this is the most important and basically the one property of a binary search tree, that each of the node, for a parent for example, the left child of a parent is smaller than the parent's value, the right child is greater than the parent's value, and that's all. That's the basic property for binary search tree. And that's why, because 4 is smaller than 12, this is why it's going to be the left child of 12. We want to insert 5, so we have to examine from the root node. It's very important, not just the middle of the binary search tree. We have to start every insertion from the root node. And we came to the conclusion that 5 is smaller than 12, so we go to the left. Because there's a child, we have to call this method recursively, we are going to implement it. So we have to check whether 5 is greater or smaller than the parent node, which here is 4. 5 is greater than 4, so it's going to be the right child of 4. We want to insert 20. So we have to examine. 20 is greater than 12, so it is going to be the right child of 12. We have to insert 1, so we keep going from the root. It is smaller than 12, so we go to the left. It is smaller than 4, so we go to the left and create a new node for it. So this is how we keep constructing a binary search tree. In-order traversal. We call recursively this in-order traversal for the left subtree. Then we print out the root, and then we call this recursively to the right subtree, and it is going to give us the numerical ordering, the ascending numerical ordering, so from the lowest value to the highest value. So here the numerical ordering, the in-order traversal, is going to give us 1, then 4, then 5, then the root node, then the right subtree, which is now consists of 1 item. So the predecessor of a node, as I said earlier, is the previous node in the in-order traversal. So for example, what's the predecessor of 12? It is 5. Why? Because in the in-order traversal, after 5 and after 5 we get 12, and after 12 we get 20. So that's why the predecessor of 12 is 5. Because it is the previous node in the in-order traversal. The successor of a node is the next node in the in-order traversal. What's the, for example, the successor of 12? It is the 20. So this is how we calculate. It's not a good calculation, but anyways, the successor and the predecessor. And it's going to be important for deletion. So, for example, we want to delete leaf node. It's very easy. We want to delete node 5. We have to search for it, and after we find it in logarithmic time complexity, of course, we have to remove it. How to remove it? We just set it to null and delete it. Okay, it's very easy, but how to delete a node with 2 children? For example, we want to remove the root node. It has a left child and a right child. We are not able to set it to null, because then the root node would be a null. It is not allowed in a binary search tree. So we have to find its in-order predecessor or successor. Here we swap with the predecessor. I use in my algorithms the predecessor, so the previous node in the in-order traversal, and we have to swap them. The 5, so the in-order predecessor, with the given node we want to delete. We swap them, then the 5 is going to be the root node, and the 12, it is now a leaf node, so we just have to set it to null. And why is it good? Because we are not, with the help of this in-order successor and predecessor, is we swap these two and make the deletion like this, we are not violate the binary search tree property. So here the root node is 5 and all of the left subtree elements are smaller than the root, and all the right subtree elements are greater than the root node, and this is the only property for binary search tree. We are not violating it, so we are good. So this is how to delete a node, this is how to construct a binary search tree, and this is how to in order traverse a binary search tree. Thanks for watching.